debt of a binary tree, given the root of a binary tree, return its maximum debt. A binary tree's maximum debt is the number of nodes along the longest path from the root node down to the farthest leaf node. So from here to here, or here to here to here, from this level to this level, this is 0. This is 1, 2, 3. So we have 3 levels to it. This one, and in this case, this is our root node, and we don't have any value for its left child, and its right child it's 2. So we get 1, 2. So let's get into it. So since we're looking at to get the maximum debt of the binary tree, we'll use a BFS binary breadth first search level by level from left to right. And let's use our Q. Q equals to let's put our root inside it and name it first in, first out. So first in, first out. So let's make a variable for our equals to 0, starting from 0. So while we have a value inside our queue, a node inside our queue, in this case we're starting with a root node. We are root node, so let's name queue. So let's loop to our queue for I, and I'll just name it underscore and queue, and the range of the length of queue. I'll just take this one out and name it level size, just so that we understand exactly what we're doing. Level underscore size is equals to this. So our level size. So while we have for every node in our level size, which is going to be the length of our queue, let's pop the pop queue dot pop first value from it, and let's assign it to our node. So this is going to be our node, so our current node. So for example, this one, if we pop it out from this will be our node. So if node dot the left, so if we have a left node, in this case we do queue dot append it to our append the left node dot left. So append it to our list. So in this case we do have it, so it's been appended here. it shows it's been appended here. So if we have a node, a right child, a child in our right node, q dot append node dot right. So in this case we do have it, and this is the child node for it. So for every one of these, so once we get out of the level size loop, let's add a depth plus equals to 1. So add 1 every time we make it to the next level if we do have it. And let's return our level value depth. So for every node in it, so once it's done with this, adding these values, then it will go then it will exit this loop and add 1 plus, and now we have these two values inside our queue, and now now it will go through the these two. So these are the two length sizes, 9 and 2 and 20. So now it's going to add a pop. It's going to pop this one out, take it out of the queue. We don't have a left child node, so it's not going to append, and we don't have a right child node, so it's not going to append. And then we're going to move to the next value and inside this. So 20, pop it out, take it out, and give it to the value, the node variable. So if node has a left child, append it, so this has been added to it, and this has been the right child, and now this one has been added to it. So now it's going to exit this loop since we don't have it. So since and then add 1 to it plus 1, and now we still do have 15 and 7 added to the queue. So queue for I and the range size, so 15 and 17. So 15 doesn't have a child, so after popping it, 15 doesn't have a child, and left child or right child. So we will exit that and come back to the second value node inside the range of size, and then this one after popping 7, there's no left child, also no right child, and then it will exit this loop, and then the for loop, and then depth plus 1. So now you also add another depth to it plus 1 and return. And now let's make if statement in case we don't have a root node to begin with. So for root not, so if root is none, return 0. That should work, and that's it. Let me submit it and see if it goes. And that's it for this problem. It's a time complexity of time complexity of O of n the 3. And that's it. And this one is an easy program to get to use know how to use the breadth first search method.